which is a clear ion process.
Good morning, students. Yesterday we have Yesterday we have discussed about the coordination number and also some of the numericals based on solids to find out formula of the unit cells. So today we have to go with another concept, that is close packing in crystalline solids. The next concept is close packing in crystalline solids. Crystalline solids. This is very important concept in solid state. Close packing in case of crystalline solids, right? Before that, yesterday I left one numerical problem. So today I'll discuss about that numerical, that problem, answers about that problem, and after that I'll continue with this close packing in crystalline solids. In yesterday's class, the last numerical was, in a cubic unit cell, A atoms are present at the corner. A atoms are present at the corner for yesterday's problem. A atoms are present at the corner, right? And B atoms are present at the face center. B atoms are present at the face center. Just I'm writing the points related to yesterday's numerical. C atoms are present at the edge center. C atoms are present at the edge center. And D atoms are present at the body center. Body center. Okay, this is the main theme of the yesterday's question. Next one, calculate the formula of the unit cell. First one, what is the formula for the corresponding unit cell? So here A is equal to corner means this is 8 into 1 by 8. This is equal to 1. B is equal to face center means 6 face center will be there. 6 into 1 by 2. This is equal to 3. C is going to be edge center. How many edge centers will be there? 12 edge centers will be there. Share of that one is 1 by 4. So 12 into 1 by 4 is equal to again 3. And D is equal to body center only 1. Body center will be there. Its share is going to be only 1. This is going to be equal to only 1. So what is the formula with respect to this unit cell? The formula with respect to this unit cell is going to be, it is A1, next one B3, next one C3, and this is going to be D1. So this is the answer related to first question, that is formula of the unit cell is going to be A, B3, C3, D, or A1, B3, C3 and D. Second question related to this problem is 25% of A, 25% of A, 50% of B, 50% of B, next one 75% of C are removed. 75% of C are completely removed from the unit cell. Then calculate the formula for the unit cell. Out of 4 different types of positions, A, B, C, D, A is corner, B is face center, C is going to be edge center, D is body center. Out of total number of corners, 25% of particles A are removed, 50% of B are removed, 75% of C are removed. After removal of all this constituent particle in the respective percentage, what is the formula of the respective unit cell? To find out the formula, first you have to identify how many particles are removed out of particle present at the corner. This is going to be A particles. What's the total number of particles present at the corner? This is going to be 8 will be there. Now this is 8 into 25% are removed, 25 divided by this is going to be 100. So this is 25 ones are 25 fours are. So this is going to be equal to, so 2 particles are going to be removed out. When 2 particles are going to be removed out in case of A. After removal of 2 particles, this is total number of particles is 8. This is minus 2 are going to be removed. So directly you can also calculate 25% of 8 means this is going to be equal to 2. Total number of particles is 8. Out of 8, 2 particles are removed. This is going to be 6. So the share of this particle is going to be 1 by 8. So this is equivalent to 3 by 4. that is equivalent to 3 by 4. So 3 by 4 is going to be remaining with respect to the particle present at corner. Next one, the particle which is present at the second one for 50% of B. B is going to 50%. How many particles present at the face center? That is going to be 6 into how much percentage is removed? 50%. This is 50 by 100. Directly also you can calculate 50% of 6 is going to be how much? It is going to be 3. This is 2. 2 ones are, this is going to be 3. This is out of 6 particles, 3 particles are going to be removed because 50% is mentioned. Now B is equal to total number of particles is going to be 6, out of which 3 are going to be removed. This is equal to 3 into 1 by 2. 3 into 1 by 2 refers to this is going to be 3 by 2. Particle present at the face centers. Third one, this is with respect to which one? Edge center. How much percent of particles are going to be removed from the edge center? 75%. Totally how many edge centers are going to be there? You know very well. This is 12 edge center into 75 by this is going to be 100. 75 by 100. This is 25 threes are, this is 25 fours are, this is 4 ones are, 4 threes are, this is equal to 9. So out of 12 particles, 9 particles are going to be removed from this one. So C is equal to 12 minus 9. Remaining is going to be 3. This is share of this particle present at the edge center is going to be 1 by 4. So this is going to be 3 by 4. So with respect to A it is going to be 3 by 4. With respect to B it is going to be 3 by 2. With respect to C it is going to be again 3 by 4. Then what is with respect to the fourth position? Fourth position, that is going to be which one? Fourth position, that is body center. Here in this question there is no anything related to body center. So D is equal to 1 into 1. This is equal to 1. One body center, it is not sharing with any of the unit cell. This is going to be only 1. Therefore, the formula of that unit cell is equal to formula. With respect to A, it is going to be 3 by 4. With respect to B, it is going to be how much? 3 by 2. Next, C is going to be how much? It is also 3 by 4. And with respect to D, it is going to be 1. If you multiply all these values with respect to 4, then formula, simplest formula of the compound is said to be, this is A3, next one is going to be B6, next one is going to be C3, and this is going to be D4. This is the simplest formula of the compound A3, B6, C3 and D4. So this is the answer related to what? The second sub question. Answer with respect to first sub question is going to be A, B3, C3, D1. With respect to second question is going to be which one? Second question is going to be A3, B6, C3 as well as D4. Clear? Copy this one. I'll go with the next question, next sub question. That is third question is also mentioned. Third question. I'll review this part. So what is the third question related to this one? C, question number C for the same main question. If all atoms along an edge are removed, all atoms along an edge are removed. What is the formula for the unit cell if all the atoms along the edge are found to be removed? Along the edge. Edge means which particle come in case of that edge of the unit cell. Just I am drawing one simple unit cell, right? This is an unit cell. What is the position of particles in case of this one? This is corner. This is corner. Third one corner. This is corner. It is also corner. This is corner. Next corner. Last corner. So in case of this one, this will be present at the face center. This is face center. This is face center. This is again face center. Front side face center. Back side face center. In addition to this one, other position of the particle is going to be. What's the other position of the particle? So this is going to be edge center, second edge center, third one. This is fourth one. This is fifth one, sixth one, seventh one. 8th one, 9th one, this is 10, this is 11, this is 12. The spots which are indicated by red color is going to be which one? That is going to be edge center. Now what they have mentioned here in case of this one, all atoms along an edge are going to be removed. This is going to be commonly called as one particular edge. So this corresponds to one edge. In case of one edge, how many particles are found to be removed? Totally 3 particles. Out of 3 particles, 2 are present at the corners and 1 is present at the edge center. Only these 3 particles are going to be removed out. After removal of those 3 particles, so what should be the formula for that unit cell? After removal of particle from the edge, if the particles are going to be removed from the edge of the unit cell, then the particle present at the face center remains same. Particle present at the body center also remains same. Only 2 particles are going to be removed from the what? The corners, and 1 particle is going to be removed from the respective edge center. Now with respect to this one, first one, if you go with A is equal to out of 8 particles, 2 particles are going to be removed from the corner. A refers to corner. 8 columns will be there. One edge means 2 particles from the corner are going to be removed. 8 minus 2 into this is going to be 1 by 8. This is 6 into 1 by 8, that is going to be equal to 3 by 4. Right? The next one, B is equal to, what is the position of the B? Face center. Face center means this is going to be 6 into 1 by 2. This is equal to 3. Here 6 into 1 by 2 we are writing as it is because particles are not removed from the face center, because the condition is atoms are removed only along the edge. C is going to be which one? That is edge center. Totally how many edge centers will be there? 12, out of which 1 particle is going to be removed. This is 12 minus 1 into, what is the contribution? It is going to be 1 by 4. So this value 13 into 1 by 4, this is going to be how much? Oh, sorry, 12 minus 1 means 11 into 1 by 4. So this is going to be 11 by 4. And D, which is present in the body center, there is no question of removal of that one. 1 minus 0, this is equal to 1 into 1. This is corresponds to 1. So the simplest formula of the compound is going to be, it is A 3 by 4. Next one, B is going to be 3. C is going to be, it's 11 by 4. And D is going to be 1. To find out the simplest formula, you have to multiply this value by 4. When you multiply this one by 4, this is A3, this is B12, A3, B12, this is going to be C11, and it is going to be D4. This will be the simplest formula of the compound if particles are removed only along the edge. That is answer with respect to sub question C. Next one. What will be the answer with respect to sub question D? What's the condition here? If all atoms on one phase, all atoms on one phase are removed. If all atoms on one phase are removed. One phase corresponds to how much? If all atoms on one phase are removed. For the same diagram, just I will show how that one phase is going to be removed completely. Just I am showing that. So this is the corner. This will be the face center. This is going to be again corner, right? And so totally same cubical structure is going to be there. The condition is if all atoms on one of the face is going to be removed out. If all the atoms on one of the face is going to be removed out, this is one more particle is present at this edge center here. If all the particles on one of the face are removed, one of the face refers to, we have to consider this is the face. One face corresponds to how many particles? 4 will be present at the corner. 4 will be present at the edge center and 1 is present at the what? The face center. So totally 4 plus A1, that is 9 particles are going to be totally removed from that particular face. Now here A is equal to, A means it is going to be corner. Out of 8 particles, how many particles are removed? This will be removed out. This will be removed out. So third one removed out. Fourth one is going to be removed out. 4 particles are going to be removed out. 8 minus 4. So this is equal to 4 into 1 by 8. 4 into 1 by 8 refers to this is going to be how much? 1 by 2. This is with respect to what? Corner. In this problem, A means corner, B means face center, C means edge center, D refers to body center. B. What is the total number of particles present in the face center? Totally 6 will be there. If the particles are going to be removed along the one face, how many face center particles are going to be removed out? One particle. 6 minus 1, this is equal to 5. 5 into 1 by 2. 5 into 1 by 2 refers to this is going to be 5 by 2. Then particles from the edge center. Totally how many edge center particles? This is going to be 12. Out of this one, how many particles are going to be removed from the edge center? This is one particle. This is second one. This is third one. This is fourth one. So 12 minus 4. This is equal to 8. 8 into 1 by 4. This is equal to 2. 8 into 1 by 4. This is the share of that particular particle present in the corner. Next one face center. Next one is going to be edge center. D. How many particles will be present in the body center? Only one particle is present. If the particles are removed from the one of the face, then there is no loss of the particle from this one. 1 minus 0 is equal to 1. The share of this one is equal to 1. This is going to be again 1. So the formula of the compound is going to be, it is A 1 by 2, next one B 5 by 2, next one C, this is going to be 2, and this is going to be D is going to be 1. Well, if you want to take the simplest ratio of this particular compound, the formula is going to be, this is if you multiply this one by 2, A1, this is going to be B5, next one is going to be C4, next one is going to be D2. So this is the simplest formula of the compound. If all atoms on one of the faces are going to be removed out. So this is about the answer with respect to 4 different answer, and number of students have posted the answers in WhatsApp in yesterday's regarding yesterday's class. Some of the students have answered correctly and some of the students are unable to get the answer. So just you try to understand about this problem. So this type of questions will be there in case of competitive examination. Probably they may not ask in case of board examination, but in competitive examination, so these problems may be asked. Clear? Okay. So next we are moving on to another important concept, that is close packing in crystalline solids. So how the arrangement of particles or the spheres or the lattice points in case of crystalline solids, that we have to discuss. Close packing in case of crystalline solids. In this concept, close packing in crystalline solids, the arrangement of constituent particles in crystalline solids we have to discuss. Here we have to discuss about close packing in case of crystalline solids in 1 dimension, close packing in 2 dimension. In that one we come across with again 2 types, spiral close packing as well as hexagonal close packing. After that we have to discuss about the close packing in case of 3-dimensional structure. In that one we come across with a variety of structures, different arrangement of structure. We come across with the 2 important voids also. Void is nothing but an interstitial position present in solids. One is called as a tetrahedral void, next one is called as octahedral void. We have to discuss in detail about that tetrahedral as well as octahedral void. When we are arranging different types of spheres in different stacking layers, different layers, we come across with hexagonal close packing as well as cubic close packing. Hexagonal close packing and also the cubic close packing, that is also we come across here. After that we have to discuss about even the location of voids, location of the tetrahedral void as well as octahedral void in case of FCC structure. So how to identify the presence of the tetrahedral voids and octahedral voids in case of face centered cubic unit cell. So these things we have to discuss, and based upon this one, we come across with some of the simple numericals. So first we'll discuss about the concept related to this close packing. Afterwards we'll consider the different types of numericals. Right. Close packing in case of these particular crystalline solids. So first one we consider the close packing in case of one dimension. First one, number one, this is close packing in one dimension. How the particles or the spheres are present in one dimension. Close packing in case of one dimension. In case of one dimensional structure, the particular spheres or the constituent particles, those constituent particles present just one after another one like this. So this is the arrangement of various constituent particles, or you can say spheres present in different types of crystalline solids. So all those particles are going to be present one after another one. So this results in case of the arrangement of different constituent particles or the spheres in case of one dimension structure. If we consider this particular one dimension structure, if you consider this one particle which is under observation, so this particle is in contact with the two other spheres, two other constant particle. Therefore, the coordination number, already we have discussed about coordination number in yesterday's class. In case of this one, two other particles are in contact with the given particle, coordination number of a sphere in one dimension is equal to how much? It is going to be 2. Just, it is very simple. The constituent particles are present just in a linear manner. Just I will show that particular particles arrangement here. Right. Just you can observe this is going to be one sphere. This is one sphere. Like that, all these spheres are going to be present in this particular structure. So this one results in the formation of close packing in case of one dimension structure. If you consider this particle, this is the particle which is in contact with this one red sphere, and another one, this is going to be an orange sphere. So the coordination number in case of this particular one dimension is going to be equal to how much? That is equivalent to 2 itself. After this one, next one we will consider, that is second one, that is, this is very simple. One dimension is going to be simple. Particles of the spheres are going to be present just one after another one. So coordination number is going to be equal to 2. Next one, close packing in two dimension. Close packing in two dimension. How the arrangement of particles in a two dimension is going to be observed. Close packing in case of two dimension. When we arrange the particles or the spheres in case of two dimensional structure, that results in two different types. So first one here it is called as, it is known as the square close packing. First one is referred to as square close packing. Then how the particles are arranged in case of square close packing. Just you observe in case of square close packing. So these are the different types of spheres are going to be arranged horizontally like this. Below that particular particle, another layer is going to be fixed out. This is going to be another layer. Okay. Next one, another layer is going to be considered here. Next layer. So all these constituent particles are going to be touching with each other. After this, next one layer also we can find out number of different types of layers are going to be found out. So this is going to be this particular layer, first layer. We'll consider this is going to be first layer. It is second layer. What type of similarity is going to be present between the first layer and the second layer? There is no any different first layer and second layer, third layer and fourth layer. All are found to be just one over the other one. So this type of packing is going to be called as AAA type of stacking. Arrangement is going to be called as AAA type because one is going to be placing on another one. So just one over the another one we are going to be placing. So because of that reason, it is commonly called as AAA type of packing. Next one, what is the value of coordination number in case of this square close packing? Coordination number of the sphere in case of this type of arrangement is, if you observe any one particle, now this is the particle which is under observation, this is just I am marking that one with the blue color. So how many other spheres are going to be in touch with this one? This is the one sphere, this is the second sphere, this is the third sphere, this is the fourth sphere. So totally these four spheres are going to be in touch with this particular particle present at the center. So therefore the coordination number of the sphere in case of square close packing is going to be equal to 4. Just I will show with respect to one model. Just if you are observing these different types of arrangement, if you are observing this type of arrangement here, one particular sphere is going to be present one over the another one. When like that, number of different types of layers are going to be possible over this one. So one is going to be exactly present on another one. When one is going to be present on another one, so here in case of this one, some of the particular depressions are going to be caused. This depression is generally called as what? That is commonly known as void. This is commonly called as void or the interstitial position or the empty space. Commonly it is called as the empty space. Empty space. In solid state structure, it is commonly called as void. So there are number of different types of depressions or interstitial position or the empty space, or simply it is called as the void. There are number of voids are going to be possible, and coordination number in case of this particular solid is going to be equal to how much? It is going to be 4. And the percentage of occupied space, if you consider total volume of the sphere, the percentage of occupied space. Percentage of occupied space in this one is equal to 52.4%. Remaining percent, 100 minus 52.4, if you consider remaining is going to be called as, that is going to be an empty space. The percentage of occupied space in case of square close packing is going to be equal to how much? It is 52.4. And what is the coordination number with respect to this particular arrangement? That is going to be equal to 4. It is commonly known as what? Square close packing. This is results in the formation of 2 dimension. Second one in case of 2 dimension only, it is called as hexagonal close packing. Hexagonal close packing. How the arrangement of sphere is observed in case of hexagonal close packing. Arrangement of spheres in case of hexagonal close packing. In case of hexagonal close packing, just you observe clearly. So these are the different types of spheres present one after the another one. Right. These are the different types of spheres that will be present here. Now here in case of this one, the next layer is going to be present between the depressions. Probably you are getting an information difference between the square close packing as well as the hexagonal close packing. Hexagonal close packing, right? Okay. Next. Okay. So, what type of difference is going to be observed between square close packing and hexagonal close packing? In case of hexagonal close packing, if you consider this is the layer A, this is the another layer that is going to be called as B layer. Whether layer A and layer B are going to be same, here both the layers are going to be same, so this is going to be called as A type of arrangement. But in case of this hexagonal close packing, one layer is going to be present. The second layer is not present vertically on the first layer. Second layer is going to be present between the depressions of the first layer. So this is going to be again it is going to be called as A, and next layer is going to be commonly called as this is going to be B. So here the First layer and the third layer are going to be exactly overlapping one over the another one, but B layer and this B layer are going to be exactly overlapping. Because of this type of arrangement, what type of arrangement it is? This type of arrangement is generally known as AB type of arrangement. AB type of arrangement or AB type of stacking. This is going to be presence of one layer over another layer is going to be commonly called as stacking. Then what should be the value of coordination number with respect to this type of hexagonal close packing? Coordination number, can you identify? Is it possible to get the coordination number? Already we have mentioned about the coordination number in square close packing, that is equivalent to 4. Now if you consider this is any one particle which is going to be under observation, this is the particle we consider that is under observation. How many other particles are going to be in contact with this one? This is first one, this is second one, it is in contact. This particles are going to be in contact here, all this is 3. Whether this particle is going to be in contact, no. This is 4th one, this is 5th one, this is going to be 6th one. So these 6 particles are going to be in contact with a given or a said particular particle. So this is going to be arrangement, this type of arrangement gives rise to an hexagon type of structure. So it is commonly called as what? Hexagonal close packing. So because of this particular 6 neighboring particles, neighboring spheres, the value of coordination number in case of hexagonal close packing is going to be equal to how much? That is going to be 6. Then this here also there is a presence of the empty space. This is going to be commonly called as the void, empty space. You observe very clearly what type of void, what percentage of void is going to be observed in case of square close packing as well as hexagonal close packing. Whether the percentage of void is going to be more in case of square close packing or this particular hexagonal close packing, if you are observing that one, the percentage of void is maximum in case of this square close packing compared to hexagonal close packing. Therefore, the occupied space in case of hexagonal close packing is equal to 60.4%. Means out of total 100% of total volume of the respective unit cell, 60.4% are occupied by the unit cell. Remaining around 39.6% is going to be commonly called as the empty space, that is going to be interstitial position. So remember one thing, what we are discussing about the percentage of this empty space as the total volume of the unit cell. Total volume of the unit cell is going to be occupied by more and more number of spheres or constituent particle. That solid is said to be a most efficient solid. As the percentage of the occupied space wherever it goes on increases, as the percentage of the occupied space by the different types of spheres wherever it increases, that results in the formation of more stable solid. So here occupied space is going to be 60.4%, here it is 52.4%, means the percentage of void is going to be less here and percentage of void is going to be more. So in case of two-dimensional structure, two types of packing or this stacking is going to be commonly observed. One is called as square close packing, next one is called as what? Hexagonal close packing. Just I'll show this hexagonal close packing with respect to this arrangement. You can observe the presence of two layers here. This is AB layer is going to be mentioned here. If you consider the first layer as the A layer, second layer is going to be present in between the depressions of the first layer. So if you are observing this one very clearly, now this type of spheres are going to be present. In second layer, it is going to be present between the depressions or the particular interstitial position present between those first layers. So because of that reason, it is commonly called as hexagonal close packing, where the 6 neighboring particles are present. So coordination number is equal to how much? It is 6. So this is about close packing in case of one dimension and close packing in case of two dimension. In close packing in two dimension, we come across with the two structure, square close packing as well as another one, hexagonal close packing. Try to understand this particular concept. Clear? Just I'll remove this one. Okay. Right. After this one, the third point we have to consider, that is in 3 dimension. Third one, close packing in 3 dimension. Close packing in case of 3 dimension. So, whatever the different types of structures are, the solid compounds are going to be there, solid metals are going to be there, different types of solid substances are going to be there. All those solid substances exhibit this 3-dimensional structure. All real structure, all the constituent particles in case of any particular solid are going to be having 3-dimensional structure. In case of this particular 3-dimensional structure, we have to go with the different types in case of this one. The first type in case of this one is going to be, this is 3-dimensional close packing. 3-dimensional close packing arrangement is going to be somewhat different here. 3-dimensional close packing from 2-dimensional square close packing. Arrangement is going to be 3-dimensional arrangement, but that is going to be obtained from 2-dimensional square close packed structures. Square close packing structures is going to be there. Already we have discussed about 2-dimensional square close packing, how that arrangement is going to be commonly observed. Just you see here. So these are the constituent particles are going to be there. In this constituent particles are going to be next layer is going to be present just below that one. So this is going to be arrangement is commonly called as 2-dimensional square close packing. 2-dimensional square close packing, right? So all these spheres are going to be present in this particular way. Here, in case of this one, there are number of other particles present behind this one. That is going to be represented like this. That is represented like this. Arrangement is going to be completely. It is 2-dimensional square close packing only, but that is going to be arranged in case of 3-dimension. Probably this particular picture doesn't give complete or clear clarity about this particular 3-dimensional close packing. Just to observe the diagram which is going to be present in any of the textbook. So they have mentioned that in this one, the particular particles or the particular spheres are going to be arranged in the format of 2-dimensional square close packing, but it is going to be in the form of 3-dimensional structure. 3-dimensional structure means just behind this one, just behind this one, just behind this one, behind these layers, all the different types of layers, number of other different types of layers are going to be there. So those layers I have mentioned at the top, all those layers are going to be present together in format of square close packing in 2-dimensional, but that arrangement is going to be called as 3-dimensional close packing structure. So here layers are going to be present just behind another one. For simplicity, just I will show that one. Suppose if you consider this is going to be a square close packing structure is going to be there. Just behind this one, another layer of particles or spheres are going to be present. Another behind, next one, large number of spheres are going to be present in the repeated manner. So such type of arrangement is going to be known as 3-dimensional close packing from 2-dimensional square close packing. Arrangement is going to be in the form of 2-dimensional square close packing. Particles are present just one over the other one. Particles are not present in depression as in case of hexagonal close packing. But just behind this one, that picture I cannot show in this board. So just behind this one, large number of particles are going to be present. As a result, the particular lattice which is obtained from this one is going to be simple cubic unit cell is going to be obtained. Simple cubic unit cell. Just you can observe this is one particle. Behind this one, another 4 particles are going to be there. These 4 spheres, and behind this one, another 4 spheres. Totally, those 8 spheres constitutes what? The simple cubic unit cell. This is not so important Just try to understand that these spheres are going to be present here. Behind the spheres, another one set of spheres is going to be there. Like that, large number of spheres are going to be joined together. That results in the formation of simple cubic unit cell. So this type of arrangement is going to be known as three-dimensional closed packing, which is obtained from two-dimensional square closed packing. Just to write this one, we'll go to next one. The second one is known as after three-dimensional closed packing from two-dimensional square closed packing. Just I'll go with the second type of arrangement. That is most important. Second type of arrangement is going to be most important one. Number 2, this is also three-dimensional closed packing. Three-dimensional closed packing from two-dimensional hexagonal closed packing. First we have discussed about square closed packing. Next one, arrangement in case of hexagonal closed packing. In this one, number of types we have. First one, placing second layer over first layer. Placing second layer over first layer. You need certain amount of patience to understand all these things. Patience is going to be very important here. First, already we have discussed about the three-dimensional arrangement by using two-dimensional square closed packing. Now, arrangement of the spheres in three-dimensional manner, but that is obtained from two-dimensional hexagonal closed packing. In this one, first type is what we call as placing the second layer over first layer. Second type will be there. After this one, we have to go with placing the third layer over the second layer. Just to observe carefully here. What is the meaning of placing second layer over the first layer? See this one clearly. These are the various type of spheres. Hexagonal closed packing means this is going to be hexagonal closed packing is going to be there. Means second layer of spheres are going to be present in the depression of the first layer. Second layer are present in the depression of the first layer, right? Okay. You can, if you want, you can go with another particular layer. Another layer is going to be, you can draw it. Right. So this type of arrangement is simply, if you go with a two-dimensional, what type of arrangement it is? Hexagonal closed packing. Why it is called as hexagonal closed packing? If you consider this is a sphere which is under observation, it is in contact with these particular 6 spheres that results in the formation of an hexagon. So it is called as hexagonal closed packing. In this type of layers, placing the second layer over the first layer. When you place the second layer over the first layer, what type of arrangement is going to be observed? So the first layer is going to be commonly called as that is going to be indicated by the blue color. Second layer I am placing over this one. Second layer is going to be with respect to this particular red ink. Now here these are the different types of spheres I am placing over this one, that is going to be indicated by this red color. When these particular spheres of the second layer, that is going to be by red color, if it is going to be placed over another one, that results in the formation of different type of arrangement. When we place the second layer over the corresponding first layer is going to be having completely blue color, one over the another one. This type of arrangement is going to be, this is A, this is B, and this is going to be AB type of arrangement. About that already we have discussed. So over this one, if you are going to be placing one more layer, over this one, if you are going to be placing one more layer, then we come across about certain type of voids or the interstitial space is going to be created. Voids or the interstitial space is going to be created. What type of voids we come across here? First type of void is going to be known as the tetrahedral void. How the tetrahedral void is created? When second layer is placed over the first layer. Tetrahedral void. Just to observe this one. Just I am numbering here. This is the first sphere. This is the second sphere. This is going to be third sphere. All these three spheres are going to be present in which layer? First layer. Fine. Another one which is going to be indicated by the red color, that sphere is going to be present exactly in between those three spheres of first layer. 1, 2, 3 are going to be present in the first layer, and fourth one, I am marking this one, fourth one is going to be present exactly over those corresponding spheres. Here, just once again I'll clarify that one. This is the first layer particle is going to be there. These are the first layer spheres are going to be there. Over this first layer, we are going to be placing another one particular sphere. When another sphere is going to be placed here, whatever amount of void is going to be created here, this void is commonly known as what? The tetrahedral void. TV. Tetrahedral void is going to be created because of the totally how many spheres? 1, 2, 3, and this is going to be 4. When 4 spheres are going to be in contact with each other, that results in the formation of a tetrahedral void. Generally, the tetrahedral void is going to be indicated as, just you can observe, this is going to be the arrangement of an tetrahedral void. This is going to be the arrangement of an tetrahedral void. So this tetrahedral void is going to be obtained as a result of 4 spheres which are going to be in contact. Just I'll show that arrangement of the corresponding tetrahedral void. Just you can observe, these are the 3 spheres are going to be there. These 3 spheres are going to be indicated by this first layer. What I have mentioned here, 1, 2, 3. Between these 3 corresponding spheres, some amount of empty space is going to be there. When we place another particular sphere, that is going to be indicated by red color. Here also I have taken red color. When another sphere is going to be placed over that one, whatever the empty space is going to be created here, that empty space is commonly called as what? The tetrahedral void. So it is a tetrahedron. It is obtained because of the placing of the second layer over the first layer. When one of the particles is going to be present between this interstitial position of the 3 spheres of the first layer, that results in the formation of one void. It is commonly called as tetrahedral void. So after this tetrahedral void, one more type of void generally we come across, that is known as the second one, octahedral void. Octahedral void. How this octahedral void is going to be observed in case of this arrangement? Both the tetrahedral void as well as octahedral void are going to be obtained because of the placing second layer over the first layer. If you are observing very clearly in case of this one, just to observe here, this is the corresponding, just I am mentioning some of the spheres here for my according to convenience. Just to observe this particular spheres, this is one, this is second one, this is going to be third one. These spheres which are indicated as 1, 2, 3 are present in which layer? First layer. Fine. Another particular sphere, this is going to be one, the red color. This is going to be second one, that is also red color. One more sphere I am drawing here. One more sphere here is going to be drawn here. So this is going to be called as the third sphere present in second layer. These spheres which are indicated are mentioned with the blue color is going to be called as 1, 2, 3 are from the first layer, and the spheres which are going to be present just over the first layer, these red color spheres are going to be 1, 2 and 3 are going to be forming what? The second layer. Well, these corresponding spheres, three spheres from the first layer and another three spheres from the second layer are in contact with each other, that results in the formation of what? An octahedral void. How this octahedral void is going to be generally obtained? Suppose if you consider these are the three spheres. These are the three spheres from the first layer. Next one, the another sphere that is going to be, this is going to be are overlapping with each other. That results in the formation of an octahedral void. Just I'll show that formation of octahedral void with respect to these different types of models, simple models, octahedral void. Right. So these are the three spheres present at the first layer. These are the another three spheres that will be present at the second layer. When these three spheres from the second layer and these three spheres from the first layer, just you observe, this is the first layer and this is going to be second layer. Just you can observe this one. When those particular particles are going to be present at the depressions of the first layer, then that results in the formation of what? An octahedral void. Now here, this is orange is going to be indicating about the first layer. Next one, the blue, green and white spheres are going to be indicating about the second layer. Whenever the depression is going to be caused in between this layer and this layer, that depression is commonly called as what? The octahedral void. Then white is commonly known as octahedral void. Octahedral void doesn't indicate that totally it is going to be obtained because of the 8 spheres. It is obtained because of the 6 spheres. Then white is going to be called as octahedral void. Whenever these spheres are going to be comes in contact with each other, this one gives a particular structure. This one gives a structure. This is going to be an square is going to be obtained. One sphere is going to be above and next sphere is going to be below. When these spheres are going to be in contact with each other, so that results in the formation of an octahedral structure. Probably in coordination compound you have read about octahedral complexes where one particular central metal atom present at the center is in contact with the 6 different types of ligands. When 6 different types of ligands are forming the 6 coordinate bond with respect to central metal atom, it forms the octahedral structure in the similar manner. So these are the 4 spheres present in case of this is going to be square, and one is going to be above this square and one is going to be below this square. Just have already mentioned about that one. If you consider these corresponding spheres here, if we consider these corresponding spheres in case of this one, after considering those particular spheres, if you consider this one is going to be 4 are going to be present at, just you can observe here, 4 are going to be present at an square. Just you can consider this one. Right. If you consider this one, 4 are going to be present within this square. This you can observe here. If I mention here, these 4, 1, 2, this is 3, this is 4th one. These 4 are going to be present in one plane. This is going to be above the plane and this one is going to be below the plane. So when these particular constituent particles or spheres are going to be arranged in this manner, this one results in the formation of an octahedral void. So this is the tetrahedral void which is going to be obtained because of the 4 spheres. When one of the sphere from the second layer is going to be overlapping on the 3 spheres of the first layer, that results in the formation of tetrahedral void. In case of octahedral void, 3 spheres of the second layer are overlapping on the 3 spheres of the first layer, that results in the formation of an octahedral void. So this is tetrahedral void and this is going to be called as octahedral void. This structure is going to be called as octahedral structure. So here it forms an octahedron and that octahedron is going to be generally mentioned as. So this is a octahedron structure. This you observe here. Octahedron structure is going to be observed here. Right? Right. So this results in the formation of an octahedral structure. You can see very clearly. This is the particular point which is going to be pointing towards you people, and this is a particular point that is going to be away, that is behind this one. This is going to be back side and this one be front side, and these 4 points are going to be present within a plane. These are the 4 points present within the plane. This is above the plane, this is below the plane. You can see this is above the plane and this is going to be below the plane. That forms an octahedral structure, and this is the arrangement of octahedral void. So most of these solid structures are going to be having such type of voids or interstitial positions or interstitial space. One is going to be commonly known as the tetrahedral void. Next one is commonly known as what? Octahedral void. And the formation of these tetrahedral as well as octahedral void is possible when the second layer is going to be placed over the first layer in case of arrangement is going to be two-dimensional hexagonal close packing. Two-dimensional hexagonal close packing. Then how to identify the number of octahedral as well as tetrahedral voids? Octahedral as well as tetrahedral voids. Suppose let the total number of spheres in an unit cell Pn. What's the total number of spheres are present in a unit cell that is equivalent to n? N you take, x you take, a you take, anything. Total number of spheres refers to, it is going to be considered as Z. Z means what? Effective number of atoms. For your clarity, effective number of atoms in simple cubic unit cell is 1. In case of body-centered cubic unit cell is 2. In case of FCC, the total number of effective atoms is equal to 4. Already we have discussed about that one. Suppose if we consider the total number of spheres or effective number of atoms in a unit cell is said to be n, then the total number of octahedral void is also equal to n. Total number of octahedral voids in a particular unit cell is equal to effective number of atoms. If you consider FCC structure, what's the total number of effective number of atoms in FCC structure? 4. The number of octahedral void is also equal to 4. Then the total number of the tetrahedral voids, that is going to be equal to 2 times of the spheres, 2n. Therefore total number of voids is equal to, this is going to be 3n. Total number of voids is going to be equal to how much? That is going to be 3n. N is going to be total number of octahedral voids. Total number of tetrahedral voids is always double the number of octahedral voids, and this is n, this is going to be 2n, and total number of voids irrespective of tetrahedral or octahedral, total number of voids is going to be equal to how many? That is 3 times the total number of spheres or 3 times the total number of effective number of atoms. So this is about the total number of voids possible in case of different types of unit cell. Depending upon the value of n, you can identify in case of simple cubic unit cell, in case of body-centered cubic unit cell, or in case of face-centered cubic unit cell. So this is one structure placing the second layer over the first layer. When second layer is going to be placed over the first layer, and along the decorations, if it is going to be observed, 2 types of voids we have discussed already. One is called as tetrahedral void, next one is going to be called as octahedral void. Always the total number of octahedral void or total number of tetrahedral void will be the double the number of what? Octahedral voids. In a structure, in a cubic structure, the total number of octahedral void is equal to 2, then total number of tetrahedral void is equal to, naturally, it is going to be 4. That can be understood how it is going to be 4, how it is going to be 2, or why it is going to be double the number of octahedral void. That will come to know when we locate the position of tetrahedral and octahedral voids. That will be discussed in the next class, how to identify or how to locate or how to find out or how to locate the exact position of the tetrahedral void as well as octahedral voids. Octahedral voids are generally found in case of body center as well as head center, whereas tetrahedral voids are only present at the corner of the unit cell. If I say only it is formed at a corner, it is only formed at body center and head center, it is not possible to understand. Only after complete explanation of that particular locating the position of this tetrahedral and octahedral void, we will come to know why this one is going to be double the number of total octahedral voids. That we have to discuss after next one. After this A, placing the second layer over the first layer. Next one is going to be placing the third layer is going to be placed over the second layer. That results in the formation of two more arrangements. One is called as hexagonal close packing, and next one is called as cubic close packing. That hexagonal close packing and cubic close packing, that we'll discuss in next class. Okay, just to concentrate on this one. And if you come across with any doubts related to this particular void or any particular concept, this you can post your doubt in WhatsApp group. Okay, thank you.